This is lesson 14.3. We're going to be looking at angles formed by chords and secants. So let's start with that definition. It's actually on the back here. So a secant to a circle is a line that intersects a circle in two different points. So similar to a chord we talked about in 14.1 goes from one point on the side of the circle to another, but it's a line segment, right? It stops at the edges of the circle. It doesn't keep going. So basically, any line that keeps going, that's going to be called a secant. Now, it has to hit it twice. If it just hits the edge of the circle, that's something else we'll study a little later in this chapter. Okay, but if it hits it twice and then keeps going past the edge of the circle, the vocabulary word for that is a secant. Okay, so what we're going to be doing is looking at what happens when we have two chords or two secants or whatever it is intersecting either in a circle, on the side of a circle, or outside of that circle. Okay, we're able to find angles based on the arcs that they are creating. So you can see on this first one, when the two lines meet on the inside, the two intersected arcs are AC and DB, and they have a certain specific relation to the angles that are here on the inside. Now, they're not equal to it. We know that a central angle, if I project it out, is equal to those arcs. This right here, first of all, these are vertical angles. So the angles in here are equal to each other, but they're not equal to these arcs. You can clearly see AC is smaller than DB, but these angles are going to be equal to each other. Okay, so there's a special relationship between these two arcs and then these two angles. And they're not equal because it's not a central angle. We've looked at these before. This is your inscribed angle. And we know inscribed angles, they are half the size of that arc that they create. So angle E is 1/2 of this arc DB. We're going to see how that relates to this. So because it's technically on the circle, we're going to consider it inside the circle. It's going to follow the same rules as this one. And then there's a separate set of rules that's very similar for when we have an angle formed on the outside by two lines that also go through that circle. These arcs, CA and DB, will be related to this angle. Okay, so that's what we're looking at. So the first theorem is going to be for these first two. So I'm going to go ahead and label it. This is the theorem for when the intersection of the lines is inside the circle. We'll consider it if it's on the circle also inside. So it says the measure of an angle formed by two intersecting chords is the mean. All right, we've seen that word before. It's the average. So if I want to find the mean of a bunch of numbers, I add them up and divide by how many there are. Now we're always going to be just looking at two arcs or just one. For one, it's just divided by 2. We know how to do that. But for two arcs, to find the mean of them, you add them together and divide by 2, and that finds the average. If this was 90 and this was 100, it's clearly not. But if it was, the average between 90 and 100 would be 95. You would add them together, divide by 2. That's the mean of the arcs intercepted by it and its vertical angle. Okay, so I'm going to go ahead and label it here just like I did. Angle E, that is going to be equal to 1/2. Now that comes from the mean, adding them up, dividing by 2. It's 1/2 because there's 2 of them. And it's the sum of these two arcs. So adding them together. AC, make sure it's an arc, not a line. AC plus DB. Now I'm going a little fast right here because once we boil this all down to what it is, it's very simple. You just add the arcs and take half, divide by 2, and that will give you the angle. And it's going to work a little bit differently out here. Now let's talk about why these are related. So this one, we know we just take this arc and take half for an inscribed angle. That angle is projecting out. It's creating that one single arc. And over here, we have two intercepted arcs, right? We're adding them and taking half. This is basically like if we had this arc and then a 0 arc. If you added the 0 plus dB and then took half, that's the same thing as just taking half of dB. So instead of writing it out dB plus 0, we just say half of dB. But hopefully you can see how those two are related. All right, so quick example of this right here. Example number 1. We have this arc CA is 60 degrees. That's this measure out here. Now, don't bring it in. Everybody wants to bring it in because we've always worked with central angles that goes from the center out to an arc. That would be 60. This is often some random spot in the middle of the circle, so it's not equal to 60. BD out here is equal to 82. Again, not equal to this one. That wouldn't make sense because these two angles in here have to be equal to each other. They're vertical angles. They're going to be equal, so one can't be 82 and the other 60. That doesn't make sense. So we're going to go ahead and find CQA using this theorem. CQA is this angle right here. It's going to be equal to this one. So finding BQD would be the same thing. So finding this one, CQA, all I have to do is use the formula right here. It's half of the two arcs added together. So my two arcs are 60 and 82. So it's going to be half of those two arcs. I'm going to go ahead and label it CA plus BD. So if you look back at your notes, you can see where this came from. But basically all I'm doing is taking half of the sum of these two, 60 plus 82. That comes out to 142 when I add them, and then I got to take half, and that's 71 degrees. So this angle is 71 degrees. That's what we just found. Its vertical angle is also 71 degrees. Also thinking ahead, we know these are going to add up to 360. So we could take these from 360, divide it by 2, and find out these other two angles here. You could also figure out what these arcs add up to, right? And then divide it by 2 to get that. But also, these angles next to each other are supplementary because they are a linear pair. So I could take 71 from 180 and find this angle as well. Okay, so that's what happens when they intersect on the inside of a circle. We're going to flip to the back, and we're going to look at what happens when they intersect on the outside of a circle. So this is your outside theorem. Measure of an angle formed by two secants intersecting outside of a circle is half the difference. So half, again, same formula, but now difference means subtraction. So the other side was half the sum of the two arcs. Now it's half the difference. So we're going to subtract those two numbers, take half, and that's how we get this angle right here. So we'll go back to the other side and fix our notes up a little bit. But let's do this problem first. Angle BED, that's out here, BED, that's going to be equal to 1/2. So just like the ones on the front, but instead of a plus in here, it's going to be a minus. We're minusing the two arcs that angle is creating in the circle. So 88 minus 26. Now the bigger arc always needs to go in front, otherwise we'd get a negative number. So when you set these up, make sure the bigger arc goes in front. 88 minus 26 is 62. And then don't forget to take half. So 31 degrees. Angle BED is 31 degrees. Okay, so let's use that and go back and fix our notes up on the front so that we can always look back at these. So angle E on this picture is on the outside. So it's going to be equal to 1/2 of these two subtracted. The bigger one up front, DB, minus the smaller one, CA. All right, so minus, take half when it's outside the circle. Add them, take half when it's inside the circle. Pretty straightforward if you're given the two arcs. Now, sometimes they're going to give you the angle, and you're missing one of the arcs, and you're going to have to work backwards. So we'll look at that here in example 3. All right, so example number 3, we have a lot to find, a complicated picture. So we kind of have to keep it all straight. Angle D is an inscribed angle, if you see that. So angle D comes and hits E, and then that angle also comes and hits C. So everything between E and C is the arc that it's creating, and that angle is half the size. So if I knew what this whole arc was, I would take half, and that would give me the angle. Now, I don't have this part of the arc right here, so I'm going to have to figure that out before I can answer this question. And I kind of have to piece my way through this to get there. So I'm going to start with the 93. The 93 is also an inscribed angle. It's on the side of the circle, and it projects out and creates this big arc out here from C to E. But I know this is 93 degrees, so this arc out here is going to be twice the size. So 93 times 2 is 186. So this entire arc is 186. The arc I'm looking for to find angle D is the rest of the circle. It goes from C all the way to E. So these two arcs together have to equal 360. I've got the 186 from E to C. Now from E to C on the other side, that's going to create this angle D. Has to be the rest of the 360. So I'm just going to do 360 minus 186. That's 174. So this angle, this arc out here is 174, and the angle is half the size of the arc. So you do 174 divided by 2, and it's 87 degrees. Okay, now if I'm going to go ahead and find arc BE, I kind of already have all the information I need. This part's easy. So BE is right here. I know all of this is 174 from E to C, and I also know BC is 112. So all of this is 174. This piece is 112. I'm just going to go ahead and subtract those to get BE. So 174 minus 112, that comes out to 62 degrees. So BE in here is 62 degrees. I do highly recommend in a problem like this where there's lots of things you need to answer, take your answer and put it in the picture so that you can use it like a puzzle piece to figure stuff out. Okay, CD is probably the trickiest out of these. CD is out here. If I had ED already, I'm going to have to find it later, so I don't have it. But if I had ED out here, I could take the 186 minus ED and I would get CD, but I don't have that. Okay, so what I'm going to have to do now is use the new stuff. So all of this was just inscribed angles and arcs. That's nothing new. That's from an earlier chapter. But to find CD now, I'm going to have to use that theorem. I've got this 43 degrees. It's on the outside. So that's going to be this theorem up here, the minus theorem, because it's on the outside. So this arc this arc minus this arc divided by 2 will give me 43. So how do I write that out? 43 equals this arc minus this arc divided by 2. So 1/2, and then your arcs subtracted. Bigger one's got to go first. So the bigger one is what I'm missing. It's what I'm looking for. So we're going to call that CD. CD minus 62, take half, has to give me 43. This minus this, take half, gives me 43. That's the formula. All right, so all I have to do now is kind of think backwards. You could do that in your head, or you can do it algebraically. Algebraically, what I would do is times by 2 on this side, times by 2 on this side. The reason I'm timesing by 2 is because I want to get rid of that 1/2. That's going to just leave me CD minus 62, because 2 times 1/2 is 1, so it's gone. And then this side becomes 86. Now, if you were reasoning through this, that would make sense. I'm subtracting these, and then I'm taking half of some number and getting 43. So if I want to work backwards, I would double 43, times it by 2, and get 86. And now I know that when I subtract these two numbers, I have to get 86 before I take half to get 43. So algebraically, just looking at this, you can see I'm just going to add 62 to both sides. And CD is equal to 148. Let's label it on the picture. Now to find ED, it's nice and easy. Because I've labeled my picture so well, I know that all of this arc from C to E is 186. I know from C to D is 148. I'm just missing this piece here. Together, they're going to add up to 186. So all I got to do is 186 minus 148, and I've got that piece, and it's 38 degrees. So this one is 38 degrees. Okay, next, angle C. Another inscribed angle. So it's going to project out, create this arc between D and B. That's the arc that it's creating. It's going to be half the size. So that arc that it's creating is made up of, 62 and 38 together. right? It's the 62 and the 38. So I'm going to add those together. That's 100. Now be careful, that angle, you can just look at it. It's not 100, right? It's way less than 90. But the arc it's creating is 100. The angle's half the size because it's an inscribed angle. So 100 divided by 2 means that angle is 50 degrees. This angle is 50 degrees. Now, some of you may have seen this big triangle, and maybe no one did see it, but we do have a big triangle, ACD. We know the three angles of a triangle have to add up to 180. So you already had the 43 and the 87. You could have took those away from 180 and gotten the 50 that way as well. So you can use the arcs or use the triangle. All right, last one, BED. We've got a lot going on in this picture, so it starts to look a little sloppy here. But BED is this big angle in here, big obtuse angle. It projects out to B and it projects out to D. Okay, so it's going to be half the size of the arc it's creating. That arc is the 148 and the 112. That's the arc it's creating. So I'm going to go ahead and put those together. That's 260 degrees. Okay, so this angle BED is creating an arc of 260 degrees. That angle is going to be half the size, so 260 divided by 2 is 130 degrees. Okay, so it's using a lot of prior knowledge of our arcs, our inscribed angles. The new stuff today that we just have to keep straight. If we have an angle on the outside, that angle is half the size of the two arcs subtracted. And if we have two lines intersecting on the inside, that angle is going to be half the size of the two arcs added. So we're adding and taking half when it's on the inside, subtracting and taking half when that angle's on the outside.